We're about ready to start graphing our data. First thing we need are two small pieces of graph paper, which we're going to set opposite from our data tables. I'm going to put these on the left-hand side here. We need to glue these in so that they have a flap that we can open up and see underneath, because we're going to write some stuff underneath the two graphs. So the first thing I'm going to do is, without lifting this off of the table, I'm going to fold over about 3 squares. It doesn't matter exactly, just like that. And I'm going to take a little bit of glue, and I'm going to put a small little bit of glue right along this edge here. If I could get the glue to work. Try again. I'm going to get a little bit of glue right on this edge. I can do dots or just a small thin line, and then I'm going to fold it right back down. So now this will stay there permanently, and I can open and close this very easily. I'm going to do the same thing with the second piece of graph paper. Fold over just about 3 lines. Put a small amount of glue along the piece that's exposed, and then fold it back. So I've got 2 pieces here. Alright, we're going to look at graphing our data. I'm going to graph this first column here. I've done this one in blue pen, so I'm going to use a blue pen to graph my data points. My first data point here, I've numbered time units 1, 2, 3, 4, 5, 6, 7, 8, 9, which is my maximum number of time units. And it looked like the highest value I was likely to have was around 400, so I scaled my graph to be every 20. So 20, 40, 60, 80, 100, 120, 140, 160, 180, 200, and so on. We should choose our scale accordingly. If I was putting my pieces very close together and my highest number was 200, I would probably make each one of these 25, 30, or 40 apiece instead of every 20. So we want to pick an appropriate scale. But we're going to be graphing only time and total distance. So my first graph point is at 31. So right here, this is 20. 30 would be would be halfway between 30 and 40. A little above that would be 31. So I've made a dot here, and I'm also going to circle this dot with my blue pen to show it more clearly. My next point is 70.5, so 40, this would be 60, 70 would be about halfway, 70.5, can't really tell much difference there. The next point is 104.5, so at 3 we go up to, this is 80, this is 100, 104 would be a little under a quarter of the way up, so there's my third point. 138.5 is 0.4, so this is 120, this is 140, 138.5 would be just underneath. 172, so this is 160, this would be 180, so 172 a little past the halfway point. 208, this is 200, this would be 220, so 208 is a little under halfway. The next one is 237.5 over at point number 7, 237.5, a little under 240 there. And the last one is 269.5, so 270, halfway between 260 and 280. So we come up here, this is 280, this is 260, so 270.5 about right here. Now our best fit line is not going to be a line that goes between an average. Is not going to be anything that we're going to guess on this time. This time we're going to start with our last point and draw a line straight to the origin, and we'll ignore any other points in between. We're not playing connect the dots here. We want a straight line. Now some of the points are above the line. Most of the points here are above the line, but my points may be above or below the line. I'm really only interested in this line because I'm going to be getting its slope later. For my other colors, I'm going to draw. Now I already did this in different colors here. If you did all yours in the same color, then mark your graph somehow. You can shade your header here to indicate that one of your lines would be red. You could put a little green star here to indicate that this is the green one, or you could put a box around this in orange to indicate that this is your orange graph. But either way, when we come back to this side, we're going to be drawing lines in our different colors and data points in our different colors to match the data over here. So we want to have a key for what these colors on this graph are. The way to do that is to color code our data here. We can do that afterwards, like I said, by just shading the headers different colors like this, or boxing our data, circling our data, or something like that. Now you should have 4 lines here. I haven't drawn the 4 other data sets. I only have my first line. But we want to get the slope of this line. The reason we drew the line to the last point is because the slope of this line can be determined rise over run. Since our origin is one of the points right here, our other data point can be the ending point, and then we can use our equation which says that velocity is equal to distance, total distance, divided by total time. So this is going to be the slope of our line. The rise is the distance, total distance traveled, and the run, the rise is total distance, and the run this direction is time in seconds. So over here I'm going to say the slope of my blue line here is equal to the velocity, the average velocity, which is equal to the distance divided by the time, which is equal to this number, 269.5 centimeters, divided by 8. Now the units for this are they're time units, but I just call them beats or claps. It really doesn't matter. And so I now have a slope which corresponds to the velocity, and that slope, 269.5 divided by 8, gives me a velocity rounded to, well, 3 figures here, to 33.7 centimeters per beat. So the velocity of my blue Dune Buggy trial is 33.7 centimeters per beat. Now back over here on this, I'm going to find 33.7. This is 30. I renumbered this here, but I started off, every 2 of these is 10. So each one of these is 5. So 5, 10, 15, 20, 25, 30. So this would be 35. So 33.7 is going to be somewhere in this area right here. So what I'm going to do now is I'm going to draw a horizontal line representing the slope of that previous number straight across here like this. I'm going to then plot this data, but I'm going to plot instead these data points here. Okay, so my first data point is 31. It's down here underneath the line. My second point is 39.5, so it's considerably above the line. Then I have 34, which is just a little above 33. It's actually almost right on the line. 34 again, almost right on the line. 33.5, again, very close to the line, just a tiny bit under 36.5. 36.5 is just above 35, so maybe right over here. 29 is very low, well under the line, and the last one, 32, is very close to being on the line, but just under the line right there. So this is my last data point in this set. Now remember, some of your sets may have 9 data points, and some sets may have 6 or whatever. But these are my data points, like this. Now, are they on the line or not? They certainly cluster around the line, as they should, because this line represents the velocity, the average velocity of the Dune Buggy. If I draw a line like this, and then I shade this area, I'm going to shade it with my pen, but you can do this with a colored pencil or something. I have an area under this line, and the area under this line, if I look at this number here, we know that area, I'm going to come back over to my thing here and draw a line. Area is equal to length times width. So let's look at my length here, and let's call this my length, and I know that it is 33.7 centimeters per beat, or clap. My length is going to be 8 claps, or beats. I'll call them beats here since I've got them down as beats already in my writing. If I look now at these units and look at what cancels, you'll see that beats cancels with beats, and the units that I have left are going to be in centimeters. When I perform the multiplication, I end up with 269.6 centimeters. Now, I'm ignoring significant figures for just a minute intentionally so that I can show you something. 269.6 centimeters. Centimeters is clearly not a unit for area. This is a unit for length or distance. The reason is because the axes of our two graphs were not length units. One of these was a velocity unit, length divided by time, and one was a time unit. So when we multiplied these together, we got a length and not a true area. This number right here looks startlingly like this number right here. And indeed that's true. That's because the area under the graph here is in a velocity time graph. So this is a velocity time graph. The area under the line is equal to the total distance that was traveled. And this applies whether or not this is a straight line, or if the line is jagged, or if it's a curve, or whatever it looks like. The area under the graph, if we total that up, it's going to always equal the total distance that we traveled.